In today's video, we're chasing an ultimate limit, a boundary not just of space and time, but of the laws of physics themselves, a point where our current theories break down. Our task is simple to state. What is the highest possible temperature in the universe? And the crazy thing is, to answer this, we first need to understand a seemingly unrelated question. What happens when you try to squeeze a particle into a smaller and smaller space? This simple question takes us from quantum mechanics to the edge of relativity, through black holes and all the way back to the birth of the universe itself. Along the way, we'll discover that the limit of temperature is bound up with the very limits of space and time. So buckle up and enjoy the ride. To answer these questions, we need to begin with quantum mechanics. According to quantum mechanics, particles aren't little billiard balls. They're described by wave functions, strange undulating patterns that provide information about the probability of finding the particle at certain locations. And here's the key point. If a particle is confined to a box, then the wave function must vanish at the walls of the box. This boundary condition means that only certain wave patterns are allowed inside the box. Specifically, only whole numbers of half wavelengths can fit inside, like a guitar string that only vibrates in particular harmonics. If the box has length L, then the allowed wavelengths will be given by lambda equals 2L over n, where n is an integer, 1, 2, 3, etc. Now, according to the de Broglie hypothesis, a particle's momentum is related to its wavelength by the equation p equals h over lambda, where h is Planck's constant and lambda is the wavelength. We see that the shorter the wavelength, the higher the momentum. Now, inside our box, we can use the de Broglie relation to write p subscript n equals h over lambda subscript n. And if we then sub in our expression for the allowed wavelengths, and then rewrite the expression in terms of the reduced Planck's constant, h bar, we find that the allowed momentum values are equal to n times h bar times pi divided by L. Once we know the allowed momentum values, we can then work out the allowed energy values. And because the particle in the box is free and not interacting with anything, all its energy will be kinetic. And thus we can write the energy is equal to p squared over 2m. And if we then sub in our expression for the momentum, we find that the allowed energy states for the particle in the box is given by the following blue equation. Now, it might not be immediately obvious, but this equation is hiding some fascinating insights. Firstly, we notice that only certain discrete values of energy are permitted, depending on the value of the integer n. That's to say, the energy is discrete or quantized, which is a feature of confined particles in quantum mechanics. And second, and this is really interesting, even the lowest possible energy value isn't zero. If we plug in n equals 1, we see that the particle still has a minimum amount of energy equal to pi squared h bar squared divided by 2ml squared. So why is that? Well, remember, the particle's wave function must fit entirely within the box and vanish at its edges. For the particle to have zero energy, it would need an infinitely long wavelength, which is only possible if the box were infinitely large. But an infinitely large box means the particle isn't confined at all. Because the wave function must be limited to a finite region, it can't be infinitely stretched out. Consequently, the particle must have a non-zero minimum momentum, and thus a non-zero minimum energy. In short, confinement forces the particle to carry some confinement energy. And there's more. If we look at the expression for the minimum energy, we notice something else. The smaller the box, the higher the confinement energy. And this makes sense, because shrinking the box means the wave has to squeeze into a tighter space, corresponding to a shorter wavelength, and that means higher momentum. You can see this directly from the equation for the minimum momentum, h bar pi over L. We see that as L gets smaller, the momentum goes up, and with it, the energy. And this is true for all of the energy levels, corresponding to each of the different wavelengths that fit inside the box. not just the minimum energy ground state. And we also note that the spacing between the energy levels grows as the size of the box decreases, and this is due to the n² scaling of the energy levels. Now here's where things get really interesting. As we keep shrinking the box, the particle's minimum momentum keeps growing, and eventually it gets so large that the old rules of Newtonian physics just don't work anymore. At that point, we have to bring in Einstein. And the reason is because at extremely high momenta, the particle's speed starts approaching the speed of light. And when that happens, the familiar equation for kinetic energy, E equals p²/2m, breaks down and no longer works. Instead, we have to use the full relativistic energy-momentum relation, where you'll likely recognise the appearance of the second term inside the bracket, which contains mc². This is the famous equation describing the rest mass energy of the particle. That's the energy a particle has just by existing. One of Einstein's great insights was realising that mass is a form of energy. Even if a particle isn't moving, it still has this intrinsic energy locked into its very being. Now, let's return to our particle in a box and look again at its momentum. As we previously argued, the minimum momentum of the particle is related to the size of the box by the equation P equals pi h bar over L. As the box gets smaller, the minimum momentum increases, and at some point, the first term in the relativistic energy equation, p²c², becomes comparable to the second term. That's the moment when the particle's motion energy becomes as large as its rest energy. In other words, when p²c² is roughly equal to mc² all squared. Or equivalently, if we take the square root of both sides, when pc is roughly equal to mc². So when exactly does this happen? To find out, we use the expression for minimum momentum and plug it into the equation pc equals mc², in which case we find the following purple expression. Then, if we rearrange for L and drop the numerical factor of pi, since we're only looking for an order of magnitude estimate, we find that L is approximately equal to h bar divided by mc. This gives us a characteristic length scale, built entirely from fundamental constants, that tells us when relativistic effects become significant, a point beyond which they can no longer be ignored. To give you a sense of scale, if our particle was an electron, this transition would occur at around 10 to the minus 13 meters, and this distance is often referred to as the Compton length or Compton wavelength. Now, if we look back at our energy and momentum equations, then we see that we can think of the first term inside the square root of the energy term as representing the confinement motion energy, which changes depending on the size of the box L, whereas the second term relates to the mass energy, which remains constant. And so it follows that for a box much bigger than the Compton length, the confinement energy will be much less than the rest mass energy of the particle. And so we can write that Pc is much less than mc². Whereas if the box is much smaller than the Compton length, then the confinement energy will be much greater than the rest mass energy of the particle, and we can write Pc is much greater than mc². And so we see that if we keep shrinking the box, the momentum will keep growing, and therefore so will the confinement energy. And eventually, it becomes so large that the first term in our relativistic energy equation completely overwhelms the second. In this case, we're in what's called the ultra-relativistic limit, where the particle's motion energy is vastly greater than its rest mass energy. And we can approximate our energy in this case as E being approximately equal to the square root of p²c². And if we take the square root, we find that for a very small box, the energy of our particle is approximately equal to p times c, the momentum times the speed of light. And this is the hallmark of ultra-relativistic behaviour. The energy is directly proportional to the momentum. Okay, so how does this ultra-relativistic energy scale with box size? To find out, we can combine this ultra-relativistic energy relation with the minimum momentum equation we derived earlier, and we find that the minimum energy scales like h bar c over L, where we've dropped the numerical factor of pi since we're only interested in an order of magnitude estimate of the scaling behaviour. Now, this is a really important result. It tells us that in the ultra-relativistic regime, when the box is tiny, the confinement energy of the particle keeps rising inversely with the box size. To visualise this and bring the physics to life, we can plot the energy of the particle as a function of box size over a wide range of scales between 10 to the minus 7 and 10 to the minus 35 metres using a logarithmic scale. When the box size drops below approximately 10 to the minus 13 metres, the energy associated with the momentum exceeds the rest mass energy, and the system enters the ultra-relativistic regime, causing the energy to increase rapidly, as can be seen from the graph. Now, at this stage, it's insightful and elegant to note that we can reach the same conclusion from an alternative but ultimately equivalent perspective using Heisenberg's uncertainty principle, which tells us that the uncertainty in a particle's position multiplied by the uncertainty in the particle's momentum must be roughly greater than or equal to the reduced Planck's constant. And so it follows that if a particle is confined to a box of side length L, we can equate delta x as being roughly equal to L. And then it follows from Heisenberg's uncertainty principle that the momentum must be of order h bar over L. And so we see that as the box gets smaller, the uncertainty or spread in momentum values increases. And if the box is made small enough, then the uncertainty in momentum will get so large that it would be possible for the particle to have relativistic velocities and momenta. And as we've already seen, for a particle in the ultra-relativistic limit, the relation between energy and momentum can be approximated by E equals pc, and therefore we can write the uncertainty in energy as delta E is roughly equal to c times delta p. If we then sub in our expression for delta p, we find that delta E is roughly equal to h bar c over L, and this result matches the minimum energy expression that we derived from the de Broglie wavelength approach, reinforcing the idea that confining a particle to a smaller space forces an increase in momentum and hence energy of roughly order h bar c over L. Okay, so let's pause and take stock. We've seen that quantum mechanics and relativity together reveal something remarkable about confinement. As you squeeze a particle into a smaller and smaller space, the minimum energy increases, slowly at first and then much more rapidly once relativity kicks in. From that point onward, as the space continues to shrink, the energy skyrockets. Which brings us to a natural and profound question. Is there a limit? How much energy can you cram into a tiny region of space before something breaks? And furthermore, what does any of this have to do with temperature? I mean, I haven't even mentioned temperature yet, and that was the whole point of the video, so why bring it up now? Well, here's the remarkable connection. Absolute temperature is, at its core, a measure of the average energy per particle. For example, when you measure the temperature of the air in your room, you're indirectly measuring the average kinetic energy of all the molecules bouncing around in that space. And to convert between energy and temperature, we simply use a constant called the Boltzmann's constant. The relationship is then beautifully simple. The energy is equal to Boltzmann's constant times the temperature. This relation is saying that the average energy is proportional to the absolute temperature, and this gives us a powerful way to translate between energy and temperature scales. So let's now go back to our confined particle, the one squeezed into a box so small that it enters the ultra-relativistic regime where the energy is given by h bar c over L. But now let's connect this to temperature using Boltzmann's relation E equals kT. We can then equate the two and we find the following blue expression. And if we then rearrange for T, we find that the temperature scales as h bar c divided by KL. And this equation says something truly profound. As the size of the box gets smaller, the effective temperature goes up. Shrinking the region of space increases the particle's confinement energy, and through the connection between temperature and energy, that translates to a higher effective temperature. Now, a quick note. While temperature is technically defined for large groups of particles, not single particles, this idea of an effective temperature is still incredibly useful. It provides a way to understand how energy scales can translate into temperature scales, and a similar argument to the one we've presented can be applied to ensembles of particles. And we can visualize this relation by plotting the size of the box on the x-axis and the effective temperature given by the equation on the y-axis. And we see that as the box size reduces, the effective temperature increases. So a natural question arises: is there a limit to how high the temperature can go? Or, put differently, is there a fundamental limit to how small we can make the box? To answer this, we need to bring in something new: gravity. According to Einstein's general theory of relativity, it's not just mass that causes gravity, it's energy too. More precisely, anything with energy, momentum or pressure can curve space-time. In other words, energy doesn't just make particles move, it can also bend the fabric of space-time. And this matters because, as we've seen, the more tightly we confine a particle, the higher its energy becomes. So eventually, that energy could become large enough that its gravitational effect can't be ignored. Now, to connect energy to gravity, we turn to one of the most iconic equations in physics, E equals mc squared. Now we can flip this around to define an effective mass for our particle, m equals E over c squared. And earlier, we found that in the ultra-relativistic regime, the minimum energy of a confined particle was equal to h bar c over L. And so, if we combine these two relations, we find that the effective mass can be written as h bar divided by cl. And so, if we now put everything together, we see that as the box gets smaller, corresponding to L decreasing, then the effective mass increases due to the increasing confinement energy. And so we end up squeezing more and more mass into a smaller and smaller region of space. And as we do so, we begin to approach something rather dramatic. Because according to Einstein's general theory of relativity, if you squeeze a mass m into a small enough region, then it will collapse into a black hole. And the critical size at which this happens is called the Schwarzschild radius. And the Schwarzschild radius depends on the mass according to the relation gm over c squared, where g is Newton's gravitational constant. And this radius defines the region of space within which all mass must be contained for a black hole to form. To find out when this occurs for our particle in a box, we can substitute our expression for the effective mass into the Schwarzschild radius equation. And when we do this, we find the following purple expression. And if we then simplify, we find that the Schwarzschild radius is given by gh bar divided by c cubed L. Now here is the key point. A black hole will form if the size of the box becomes smaller than the Schwarzschild radius. In other words, we reach the critical threshold of the black hole forming when the size of the box is equal to the Schwarzschild radius. And if we then sub this into our previous equation, we find that L is equal to gh bar divided by c cubed L. Next, if we rearrange for L, we find that L squared is roughly equal to gh bar divided by c cubed. And then finally, if we take the square root of both sides, we find that L is roughly equal to the square root of g times h bar divided by c cubed. And this equation represents a very special length scale, known as the Planck length. It's approximately 10 to the minus 35 meters, which is unimaginably small, trillions and trillions of times smaller than an atom, and it's believed to represent a fundamental limit, the smallest length that has any physical meaning within our universe. Because if you try to squeeze anything into a region smaller than the Planck length, it will collapse into a black hole. And now we come full circle. Because earlier we found that the effective temperature of a confined region of space scales like h bar c divided by kl. And so, if the smallest possible length is the Planck length, then the highest possible temperature will occur when L is equal to the Planck length. And if we then sub in our relation for the Planck length and simplify, we find that the maximum temperature is given by the expression 1 over k times the square root of h bar c to the 5 over g. And if we sub in the constants, we find a value of 10 to the power of 32 Kelvin. And this temperature is known as the Planck temperature, representing the theoretical upper limit of temperature in our universe. And the Planck temperature is a number so large it's almost impossible to grasp. For comparison, it's about 1 trillion times hotter than the hottest known stellar core, the kind of place where elements are fused in raging infernos of heat and pressure. Those stellar cores, in turn, are more than 10,000 times hotter than the surface of the Sun, and the surface of the Sun is already over 20 times hotter than the surface of the Earth. Put it all together, and the Planck temperature is roughly 200,000 trillion times hotter than the Earth's surface. It's a temperature so extreme that our current theories simply fall apart. Space, time, gravity, quantum fields, all of it begins to blur and break down. To go any further, we'd need something we don't yet have, a theory of quantum gravity, a framework that unites the physics of the very small with the physics of the very massive. Now, it's interesting to note that we can look at this from a slightly different perspective. Hawking radiation is a quantum mechanical prediction that black holes aren't completely black. Instead, they emit thermal radiation due to quantum effects near their event horizons, causing them to slowly evaporate. The Hawking temperature quantifies the temperature of this radiation, and if you're interested, I've made a separate video exploring it in more detail. For an order of magnitude estimate, the Hawking temperature is given by the equation h bar c cubed divided by gmk. This tells us something profound. The smaller the black hole, the hotter it gets. The larger it is, the colder it gets. This formula links gravity, quantum mechanics and thermodynamics in one elegant expression. Now, earlier we introduced the equation for the Schwarzschild radius, and if we then imagine that our black hole has a Planck length size, then we can equate the Schwarzschild radius with the Planck length. And if we then sub in our expressions, we find the following purple expression. If we then rearrange, we find that the mass is equal to the square root of h bar c divided by g. This mass is known as the Planck mass and represents a fundamental mass scale constructed out of h bar c and g. And this mass represents the mass of our Planck-sized black hole. And to find the corresponding Hawking temperature of this black hole, we sub the Planck mass into the Hawking temperature equation, and we find the following purple expression. And if we then simplify, we find a temperature equal to 1 over k times the square root of h bar c to the 5 over g, which we immediately recognise as the Planck temperature. And so we see that a black hole with Planck mass and Planck size emits radiation at the Planck temperature. So, to summarise, we've seen that confining a particle into smaller and smaller regions causes the energy and hence the effective temperature to rise. But there's a limit. Eventually, the energy density becomes so great that the region collapses under its own gravity to form a black hole. And this happens when the confinement scale reaches the Planck length, and the temperature associated with that final limit, just before collapse, is the Planck temperature. A natural upper bound, a ceiling beyond which temperature as we know it may no longer make sense. It's the edge of our understanding, and to go beyond it, we'll need a new theory, a unified description of the quantum and the gravitational, a theory of quantum gravity. And at the moment, such a theory in complete form does not exist. Before we finish, I want to take a look back to the very beginning of the universe. According to our best cosmological models, the universe began with the Big Bang around 13.8 billion years ago. In the earliest moments, everything, all the energy and matter that would one day form stars, galaxy and people, was squeezed into an unimaginably dense state. And if we work backwards, using the ideas we've explored today, we can argue something remarkable. When the universe was compressed down to a size comparable to the Planck length, the temperature would have reached the Planck temperature, around 10 to the 32 Kelvin. And we can also estimate how long after the Big Bang this size and temperature would have occurred. That moment defines what we call the Planck era, the earliest slice of time after the Big Bang, when quantum gravitational effects dominated everything. We can even estimate when this occurred. If we assume that the size of the early universe corresponds to the maximum distance a signal could travel, that is, the distance light could move, then the time it takes light to travel one Planck length gives us the relevant timescale. And this will be equal to the Planck length divided by the speed of light. If we sub in the expression for the Planck length, we find the following expression. And if we then sub in the constants, we find a value of 10 to the minus 43 seconds. And this represents the Planck time, the shortest meaningful unit of time we can define with our current understanding of physics. And it's at 10 to the minus 43 seconds after the Big Bang, the Planck time, that the universe was just one Planck length across. And at that moment, the temperature is thought to have reached the Planck temperature, around 10 to the 32 Kelvin. And that brings us to the end. The Planck time, the Planck mass, the Planck length and the Planck temperature. These aren't just numbers. They appear to represent boundary lines of our current best theories. What's needed are new ideas. And maybe, just maybe, someone watching today will be the one to unlock the next chapter in our understanding of space, time and temperature. If that idea excites you, and if you're someone who loves exploring scientific ideas and building real understanding, then you'll love Brilliant, who are kindly sponsoring today's video. Brilliant is an interactive learning app with thousands of lessons across maths, science, programming and data analysis. What makes it so effective is how it draws you in. Instead of just watching passively, you're solving problems, testing ideas and building intuition step by step. It's a far more engaging way to learn, and it's been shown to be up to 6 times more effective than simply watching videos alone. One course I'd highly recommend is Scientific Thinking. It's a fantastic starting point if you enjoy pulling ideas apart and thinking like a physicist. You'll work through puzzles that feel playful, but are designed to sharpen your reasoning, helping you spot patterns and ask better questions, the kind that lead to real scientific insight. And right now, you can try everything Brilliant has to offer completely free for 30 days. Just head to brilliant.org/physics explained or scan the QR code on the screen. You'll also get 20% off an annual premium subscription if you decide to stick around. So thanks for watching, and until next time, goodbye.